Bismillahirrahmanirrahim. Starting with the name of Almighty Allah. Today we are going to learn another construct of automatas. So that is push down automata. If you can recall these bubbles or the hierarchy of the languages, you can easily recall this. This was finite languages. Over that are regular languages, and we have discussed regular language in full length detail, or it would not be exaggeration that we have only studied by now the regular languages, in which we studied FAs, finite automata, in which we studied the three versions of finite automata, that is DFA, NFA, and epsilon NFA. Then there was another machine or the construct for regular languages, that was transition graph, and then there was another construct or machine for regular languages, that were regular expression. Okay, all these constructs, that is FA, TG, and RE, are the constructs or the machines to recognize the regular language. Over this one is context free languages that are stronger than the regular languages. That's what we are going to start today. So actually our topic is context free languages. And this context free languages have we are going to study two constructs of this one, two machines to recognize context free language. Number one is PDA, that is push down automata, that is written here, and the other one is CFG, that is context free grammar, that we will be studying in the next lecture. And then there are all rest of the languages. As you can see that it is very much obvious that all regular languages are under the hierarchy of context-free languages. So that means that every regular language is by definition a context-free language. So that means so all these languages come under this bubble or under this hierarchy are context-free languages, out of which few are the regular languages and few are the finite languages. Okay, and there are many other languages that are also not context free, that is above the hierarchy, in the above hierarchy of context free languages. So these comes here. So right now we are only concerned with context free languages and their constructs. Now as we can see that there are different languages that we have studied in the under the title of regular languages. So the question is, there any other languages that come under this context-free language? The obvious answer is yes. There are languages that cannot be recognized by these FA, TG, and RE, but they have their own construct, that are PDA and CFGs. And these machines are definitely more powerful than the machines that exist for the regular languages. So PDA is basically an automata with stack. So that's why, because this push and pop operations are related to the stack, so that's why this is called the push down automata. So you can say that push down automata is a simple automata that we have studied previously, but it is having a stack, so you can use it at any time to put the numbers or values in the stack and then pop it again back. This automata is basically more powerful than the previous automata. It's having a extra stack that is uh, actually the memory, so we can use it for calculations, for the execution of the machine. It would be very much helpful. So to represent this automata we need a new format for this one. So that's what we will be starting our lecture with, this new format. So how it is new, so what are the new symbols to represent this one, and how we can convert an existing FA into a PDA. The first difference is the input tape. So it is an infinite tape, so you can see here, so it would look like something like this one. And it is used to be to place input strings on it. And after the end of the input string, so legal input string is A B A, and till the end of this tape there would be infinite deltas that you need not to place, but it always stay there. Whenever you place an input, after input, in from starting from the next cell till the end of the tape that never ends, it will be carrying deltas. The input tape is supposed to accommodate all possible strings. The input tape is partitioned with cells so that each letter of the input string can be placed in each cell. So here you are placing these cells values in the each cell. The input string ABA is shown in the following input tape, just like this one. It is assumed that when you read the first delta, so reading from here towards the here, when you read the first delta, so it is supposed to be that the string that the input string ends here and the rest of the tape is empty. So the initial point is converted into the star. It's an oval shape, just like the flow chart. So PDA is more like a flow chart than a graph. So our finite automata was more like the graphs that we have studied in data structures. So your PDA is more like a flowchart. So every PDA will start from the start state. So the start state is equivalent to the minus in the FA or TG, and at the same time will never have incoming arrow, so only have one outgoing arrow. The next change is the accept state. Accept is equivalent to the plus of FA and TG, that is the final state, and it will never have any outgoing edge. And the next is the reject state. It is equivalent to non-final dead state. So once you enter into this one, you cannot leave this one. So it will never have any outgoing edges. The next is the read state. So this is equivalent to your simple state in FA and TG. So this state is represented with the diamond shape. So you know that the diamond shape is always used for the decision making in FAs. So here it is same, when you read it, then it makes a decision according to the input. So there would be output arrows with the label, so the path would be opted according to the input letter that is read at this level. So this is equivalent to the state of, that is circle, then represented with the circle in FA and TG. So this can be replaced with the that one. For conceptually you can understand it that way. So the pop symbol extracts a symbol from the stack, and it is having all incoming and outgoing edges, just like the read state. So it is having all incoming and as well as the outgoing edges. So in the same way, stack pop is also having incoming and outgoing arrows or edges, whatever you call it. The next one is the push. Push basically pushes are toss symbol on the stack. So toss symbols are different from the input symbols. They are special symbols to place on the stack. So they can be the same ones, but this is an independent set, and this set can have the same symbols as the input symbol set. And finally, after discussing, I would like to discuss the stack. That is something that has one open side and one is closed side. So last in, first out. So these two operations, push and pop, are obviously related to the stack. So stack is an one-sided infinite memory in which you place, so it is last in, first out. At the same time, when you extract the last symbol, when the stack is empty and you extract and you pop when stack is empty, so it sends you back delta. So you can say that at the bottom of the stack is delta. So whenever the stack is empty and you pop something, it always give you the delta. When you push it, so you can push simply whatever the symbol you want to place on the stack. So it can be the input symbol or it can be from the tau symbols. So if the tau is different, then it can be that one, and if tau is as the input symbol, so even then it is from the stack symbols. And finally, as any symbol, so this is the alphabet. You are very much familiar with the with this symbol. So this is the same input symbol set. So so there are two symbol sets. One is inputs, that is sigma, and one is tau. Tau is basically stack alphabet or stack symbol set, whatever you like to call it. So whenever you place some symbol on the stack, so it should be from the top. Just remember this thing. Just revising all this one, this is input tape where you place your input symbols, where you place your input symbol, that is the word. And just like the minus sign in the FH, you have the start, then you have the accept, two halt states, that is accept and reject. So they will never have an outgoing edges. So just like the state in FA and TG, so it's being switched to this decision making state, diamond shape state, and that is read. Then to extract from the stack you have pop, from to place some symbol on the stack you have push, then you have stack, then input symbol set, and then tau, that is stack in symbol set. So now let's see whether we can convert a simple FA into PDA or not, so that you can see that every language can be every regular language can be identified with PDA. For that one, we are going to see how we can convert an FA into PDA. So step by step we are going to do it, and if you can recall it, or you have notes of the last part of this video, so you should be having all the equivalence in these of these symbols that are being here in this one. So starting with the initial symbol, that is minus, so you convert it into start. So this is start. You have convert. So now we are going to convert this state A. So I think you can guess that this A is going to be converted into diamond shape read. So for this one we convert it into a read state. So this is read state for this A and it is having a self loop. So we are going to convert this one into a self loop. So how easily we can do it, you can see, and the self loop is on the input symbol 1. So if you read the tape and you get a symbol A1, you can have it like this one. Now there is another state here, so this state is converted into another read. So here we convert this one into another read. So now there are more than one read, so we can mark them as read 1, read 2, read 3, or just like I'm marking it like read A and read B, just to make a clarity while discussion that this one is a different read, this one is a different read. Now you can see that I'm talking about this arrow right now that is marked. So it is moving from read A to read B. So this is going to have the same arrow like this one. So it's okay. This one is clear now. So this is read A. Sorry, not read A. So it's read 0. It's not A. It's 0. Okay. So it is 0. And now talking about this one with 3 lines, so it is moving back to A. Okay, so I move it back to A. So this is moving back with 1, sorry. So it gets, if reads 1, so it goes back to this one and then move to the read A, and then if it gets 0, it move to the read B. Now here we can see that the sigma of this FA is 0 and 1. So from this read you can see that it is having a label at 0, it is having a label at 1, so both labels are complete. So now there is another symbol that can come, that is on the tape. So whenever you have some input symbol, whatever it is, if you are having some inputs as 0 1 0, then rest would be deltas, and this delta will be telling you that the input is complete now. And here if you just like here, if your input ends here at this state, so it is definitely invalid word or the rejection of that word. So here we do it formally. So at this rate, if you get a delta, so that means it is the end of the input symbols. So you reject it. It is the same thing that you do here. So here you are formally announcing it that this word is rejected. And here if you here you can see that this is the final state. So if you get a delta here, so that means your input ends here, so you are going to accept it. Okay, so there is another loop, I forgot to mark it, so let's mark it now. So that loop is on 0, so this, because this label is 0, so we can place another label here. If it were 1, so we should be marking some other path. We cannot put it on this flow. So this is how every FA can be converted into a PDA. Remember one thing, that please do not confuse these deltas with epsilons. So this is basically, if it is coming from the from the in read state, coming out from the read state, so it means that the input is finished here, just like here, just like here, and it can only move to accept or reject states, moving towards the accept or reject states. Okay guys, so I'm giving you this FA. It is very much easy, so you can convert it into PDA. I think you should do it. Stop this video right here and try to convert this one into a PDA. I just giving you the hint that this minus is going to be converted just like the start in this one. And okay, so this is a loop, so it is going to be the same loop like this one here. So at the input symbol 1 it is going to be, it's an input symbol 1 is going to be, then there is a infinite, there is a self loop. So it would be, there would be a state here, and then it would be rotating around itself. Then there is a loop between B and C, it would be just like this one, that is read between read 1 and read B2. So remember one thing, in this scenario there are no more than one input state, acceptance and reject. There can be more than one accept and reject states. So remember, you can mark them with accept 1, accept 2, reject 1, reject 2, so that it can be clear for the explanations. Okay, guys. So few words on the context-free language and the regular language. What are the differences between the two languages? So regular languages, we have studied that they are something like this one. Their regular expressions look like something like this: a star, b star, a into b plus c star whole star, a b star whole star. So something like this, in which you have infinite loops, and then that can be opened as many as this loop can iterate as many times as you required, or the length of the word is required. In context-free languages, basically you can see that there are, again, this is a loop, a raised power n is a loop, b raised power n is a loop. But you can see that these two loops are not independent. So if I mark it a language here like a star, b star, so this language very much looks like this language. But in this language you can have words like a b b b b, a b b, a b. So all these words can be there in a star, b star, because the number of the occurrence of number of a's is not dependent on the occurrence of number of b's. But in this language you see that the power is the same, so it means the number of a's and number of b's are to be equal, so they cannot be different. So in this one, you can say that the first A and the third A, they are, they have the dependencies. So if there are two A's, then it should be having two A's. But the number of B may be any number. B can be any times repeated. So here, context-free languages are the languages in which you have some kind of dependencies of the occurrence of one symbol on the other symbol. And so that is why that when you need to go for such kind of language, you need another extra space to store a's before moving towards the b. So whenever you have to reach b, so you would have read all a's before that. So you place B, all A's in a separate place, and then when you read one B, you dispose one A. When you read second B, you remove second A from that extra space, and so on. If at the end you have removed all B's, and then you find that the all A's are also removed, so then you can say that this word was belonging to this language. Otherwise, if there are a's remaining or the b remaining, so there are, that means that two symbols are not in equal size. So it means that word was not from this language of a and b. And okay, so let's draw a pdf for a and b. And no, we have to start it with the symbol start. First of all, we have to think about its logic, how we are going to do it. So we have input symbol set. We have to define the, let's take a language a raised power n, b raised power n, and construct its PDA. We know we have symbols stack that is having delta at the bottom. We have infinite input tape in which we would be having symbols, and at the end it would be filled with the deltas. So let's have a word double A, double B, and then there are different deltas on this one. uh, we have input symbol set sigma, that is looking at this expression. We can see that input symbols are A and B, and then we have tau, that is the symbol that we are going to place on this on the stack. Now we can see here that a raised power n and b raised power n, so b will not start until a ends. So there are few words like ab, double a, double b. So if you start reading, then you will be getting a, then b, then b. So you cannot have the mix of this one like a b a. So this is not the part of this language. So keeping all these things in mind, so we will first of all you should construct at least 10 words, 10 legal words and 10 illegal words of this language, so that you can understand how it is going to generate words and what are the illegal words of this language, because all your PDA is going to depend on all this information that you will get from the set of valid and invalid words. So the first thing you need to do is you have to start your PDA with a keyword start. Now then you will on this symbol set, symbols are on the tape, so you start reading this one from A until you get some B. So first what you need to do to calculate whether there are equal number of A's and B's, what you do is you put all A's on the stack, and then when you start reading B, then you will be removing A's from this one. So at the end, if you get this symbol delta on the tape and you get this symbol on the stack, so it means then your input symbols were of equal length, that is the number of A's and number of B's were equal. So keeping in mind all these things, so first what we have to do is we place all these A's on the stack, because there's dependencies on the number of A's and number of B's, so those both should be equal. So first we do is we read this symbol from tape, so let's call it read one, and then we push it on. So consciously I'm going to change the push symbol, so I can push A here, but I'm going to push it with X, so my tau is going to be X. So we need to read until we get some other symbol. So we read A, then we push X. So that means we are going to push X here, push X here, push X here, when until we get some B. So this is going to be a loop. So we are going to mark it as a loop here. So moving back to the top position. So moving back to this one, so the flow moves like this one. So this is basically a self loop in the previous format of FAs. So this is so you are reading and pushing X, you are reading and second A, and then you are pushing second X, you are reading third A and you are pushing third X. At some moment you will reach at a point then that you read some B in place of A. So as soon as you read a B, you have to pop a symbol, that is the 1x that was placed on the stack in place of a. So you pop it, so let me call it pop 1. You read a pop, and then what you need to do is, so this pop is catered with this first b. You read the first b and then you have popped, and if you get an x from that one, if you read the x, so this one set is completed. So that is against this b, you have against this b you have read this first a that you have already read, but you have cancelled this one first a. Now you will go to the next b, so that means you need a loop on this b's also. So that's what we are going to do. For that purpose, if we have another b, because this is going to be independent, if we mix up with this one, so then it means it's going to accept ab kind of input also. So this has to be different from this, the acceptance of a's. So it is going to accept only b's. So we read 2, and if we get a b, we move back to this place, and then we pop this one. So the first pop was along with this b, then next pop is, then we read b and then we remove 1a. We read and then remove, we read then we remove. Now we need to understand that we are reading b from here and then popping here, and it should be x, because we have to corresponding with 1 to 1 correspondence with 1b, and remove 1a, reading 1b and removing one symbol from a that was placed in place of a. So then reading second, then removing second symbol from stack, and so on. So if at this moment you read a b, then there should be a symbol that should be removed along with for against this b. So if you get a delta here, so it means this is not the normal scenario. So it should be giving you x for the normal scenario, but if it is giving you delta, it means your a's were in less than the b's. So you just reject it. Okay, hopefully you can understand, because for this b there should be one x, but if you have read one b and there is, the stack is empty, so that means b's were more than a's. So you have to reject it because your stack is empty. So there is no, and at a and b are not in equal sizes. Now what if your input tape is finished? So that it means then at read 2 you will be having delta on the from the input tape. So it means now you have to check whether the stack is empty or not. So you place another pop here, and you will check what symbol comes out of pop. So if it is delta from the pop, then you are going to accept it, and if it is not delta, and it is, if it is x or some other symbol, then it means the number of a's were more than number of b's. So you just reject it. So let me call it reject 2, and this one is reject 1. Now let's check few more a little bit deeply. So if you get a delta here, so that you are reading a's and then there comes a delta, no more b's, not even a single b. So it means you are going to reject it. So let me call it reject 3. And at this point, if you get during the reading of B, so there should not be A. So but if there's occurs some A, so that means it's going to be an invalid scenario, so you should reject it. Let me call it reject 4. So in this way, you have to, after completing your PDA, you have to check it with the other symbols, whether there is some path that is missed or not. So you have to check for every possible input and every possible path in that one. Let's do a straight run so that you can understand that how this PDA runs on this input symbols. So it always starts with the symbol start. So this is start. Then you move to this read 1. So read 1. So at this read you read this A symbol, this symbol A. So read A, then you push X. So this is delta, so you have pushed X here. So read, that is A, and then you push X. Okay, so then you moving back to this read 1 again. So after push you go back to read 1 and then you are basically here after reading this. So you're reading A, so at input A you are pushing X, so you have input A and then you have push X, so you have push X here. Okay, so you have pushed second X here. Now after pushing X you are again back to read 1. So I'm writing read 1 down, read 1. So you can see what next character you are going to read, that is B. So here you are now read 1 here, so you read B here, so you have read B here. So how you will be moving read 1, so you are moving from this one to this pop 1. So it means now you are at the state pop 1. At pop 1 you are going to extract 1x. So you are popping some symbol, so the symbol you are popping from here, from this stack, is going to be this X. So you have removed this X, so you got X, so now you are moving on the symbol X. Now you are going to read 2. So you are reading 2 and you are getting this one is B, and then you are moving back to pop 1 and you are trying to extract this symbol. So now the top symbol is X, this one, so it is removed. According to the X you are moving again to read 2. Then at reading 2, so what are you going to read? This read, you are reading delta. So at this stage you can see to reading delta, so you are moving to pop 2 here, so you are moving to pop 2. And at this one you are going to read this delta. So you are reading delta, so then it means you are going to accept. So this is the delta you are going to accept. So this was a valid input. You can try different inputs like uh, try these inputs. So it should be A, B, B, B. It can be A, B, A. So it can be A, B, B. It can be A, B. So these invalid inputs will really help you to handle the errors of this PDA. So there may be some error in this one because I just tried to do it on in front of you. So go for these invalid inputs and you will be finding step by step you will be improving your PDAs. So this is how. So if you ever face any problem during this lecture, please do comment it, and I will be checking those comments and then I will be answering those one. Just mark the time at which you face some problem. So please go through it at least twice so that you can understand and grab and remember every concept in this one. uh, Hopefully you can draw the language, mod language on this one. And then so I give you few examples of other languages, so you can do attempt these languages like an, bm, in which a and first a's and third a's are dependencies. There can be there can be an infinite loop on b. So a would be placed on stack, and then at the third is, so stack symbols are removed with every a. So let's have a and bm, where m is equal to n plus 2. So that means it would be some very much like the a and b in fa, sorry, PDA. So after that, after the end of a and b, and you are going to have two more b's that would be checked, just read and then removed. You can have language like a and bm, c n plus m, and so on. So you can make your own language. So you are in this language, you will place a's and b's on the stack, and along and with the c's you will be removing stack symbols one by one. So this a and b and can express, you can discuss every language in terms of a and b n language. So if you can understand this one, so you can easily draw the other PDAs too. So please do ask questions and don't hesitate in any way. Thank you guys, thank you very much.